Okay, so we're starting with this. This is the third video, and this is a mass spec. What a mass spec basically does, it's a very simplified version. But a mass spec will accelerate and ionize particles put into it. And as it shoots them out, they basically hit a wall. Okay? If they're too light, they just fall off, or they're too heavy, they fall off. If they're light, they go flying into the wall. And then we detect where they hit. And depending on where they hit, we get these lines. And if you have done the Candium lab already, then you know these lines we measure and we can get relative abundance from them. So, on the isotopes, the atomic weight, how do we determine the atomic weight of an isotope? Well, we get that chart and then we see how high it is compared to each other, and we find out what the mass was and how many times it hit there. So we change that percent into a fraction, and I like to do it at the end. You can do it whenever you want to, but I just leave it as percent because that's what they usually give it to you. And you take 34 times 75.78 plus 36 times 24, add it together, divide by 100, and you've got your answer. So you can divide each of, or times each of them, add them together, and you'll get your answer. It should be between the isotopes that you've been given. If it's not, then you did something wrong. And so that's always a nice thing to remember. And since the mass was only weighed to 2 after the decimal, and we've added, we should only report for total significant figures. Okay, so let's do some more. So again, I wait till the end to that example that was right here was from your book. I like to wait till the end to divide it by 1,000, or by 100 to get it out of percent, so I just save time. So I like to take 92.21 times 27.9769 plus 44.7 times 28.9765 plus 3.009 times 29.9738, enter, then divide by 100, and I've got my answer. Okay, so go ahead and do that and see what you get. So I'm going to sort of put my little time signs up here. And then plus, times these two together, plus, times these two together, plus. Then you're going to get an answer. Once you get the answer, divide it by 100, and you've got your final answer. So I'm trying to grab a calculator real quick. If you've got your answer already, you're ahead of me, which is awesome. Let's see how well you did. So 92.21 times 27.9769 plus 4.7 times 28.9765 plus 3.09 times 29.9738 equals syntax error. Great. Okay, well, I'm going to let you do that. I'll quickly figure it while you're doing the next examples. So, moving forward. So take a time and really quickly do these. And I guess I can't go back. So it should have been between, I'm just going to flip back real quick. It should have been between 28 and 30, and it looks like it was a lot closer to 28. So 28 point something is what you should have ended up with. So now go ahead and do these, and I'll do them with you. So on this lithium, you should have ended up with 6.9417 is what I've got. Remember again, times these, plus times these, and then equal, divide your answer by 100, and then you should have ended up with 6.9417 U as your answer. Okay, go ahead and do the bottom one again. Times, plus, times, equals. Take your answer, divide it by 100. I love this board on this corner. And then equal. Which one should we end up closer to? Hopefully 63, because that's more percentage-wise higher. So you should be able to double check your answers that way. Okay, I got 63 point, and we're going out to 4 after the decimal, 5474. So hopefully that's what you've got. All right, moving forward. On the periodic table we have groups and periods. Groups are columns. Now you'll notice the white area at the bottom. There's a white area in the center right here. That whole thing, there's 40 of them, is a family. This row is a family, and this row is a family, the actinide and lanthanide. So the columns are numbered 1 through 18, and the periods on your periodic table, you can go ahead and number down by the side of it, 1, 2, 3, 4, 5, 6, 7. Those are our periods, or shells out from the nucleus. There's 7 shells that we know of. So as we're looking at the families on the periodic table, this is basically the families, and you'll need to be aware of what these families' names are. So if you would like to write them down on your paper, that's great. Probably not a good idea to put them on your periodic table because we'll be doing other things with the periodic table. But go ahead and write them in your notes. The first column is alkali metals. Second column, alkali earth. The middle one is the transition metals. The bottom 2 are known as intertransition metals, also known as the lanthanide and actinide series. So sometimes they're just called this, but when they refer to both groups, they call them the intertransition metals. The column 13 is the boron family. Column 4A or 14 is the carbon family, then the nitrogen family, oxygen family, also sometimes called the chalcogens. Then the halogen family, and then noble gases end on the very end. All right, so when we look at different characteristics, and this is where we need to break it down and talk a little bit about each family. 1A and 2A have similar properties. The song that, if you listen to ASAP Science, the periodic table, it talks about 1A, are alkali metals and halogens reacting explosively, and they do. You put alkali metals in water and they react rather violently. Alkali earths react with water, but a lot slower. So properties of both groups that they have, they're both soft and shiny. They have low melting points. They're good conductors of heat and electricity, and they react with water to form basic solutions. This is the alkali metals. What we were seeing were the alkaline or alkali earth metals. Alkali metals, both of them are not really found alone, especially alkali metals are not found alone in the world. We have to usually separate them out. Okay, the alkaline earth metals, beryllium, calcium, down, strontium, barium, and radium. There's some pictures there on the bottom left. They are different from the alkali metals. Alkali metals have 1 valence electron. Group 2 has 2 valence electrons, and we'll talk about valence electrons in a minute. They're harder than Group 1 metals. They're less reactive than Group 1 metals, and they have a higher melting point than Group 1 metals. The reactivity for Group 2A elements also increases from top to bottom. So as you get bigger, they are more reactive. That's the same with column 1. As we look at halogens is one that you're going to need to know a lot about. The most reactive is actually fluorine, so it goes opposite of what the alkali metals did. It becomes more active as you get towards the top. Chlorine is a gas, bromine is a liquid, iodine is a solid. So you've got all phases in one family, and this is the only family that has all 3 phases. It's never found in lone nature. It's very reactive with the nonmetals. They will react with almost every nonmetal. They exist as two atoms joined together for most of them. Astatine we don't know about. That's the only one. And then they have 7 outer shell electrons and react violently with alkali earth metals to form salts. And that gives us our 10 minutes, so I'm going to stop it right here. And this is your third video.